everybody. We are here with 3.6 notes, deviations from the ideal gas law, and I am Miss List bringing this to you today. One of the things that gets kind of glossed over in regular chemistry, if you've had a first year course, is what exactly is an ideal gas and why do we call it the ideal gas law? Well, in order to understand those things, you have to know a little bit about kinetic molecular theory, which is why we covered that in 3.5. And now here we are at 3.6, which is titled Deviations from the Ideal Gas Law. So gases behave ideally under ordinary conditions. And we call ordinary conditions high temperatures and low pressures, because technically ideal gases don't exist. It's fictional. Now, gases can behave ideally when they have high temperatures, which means they're going to move fast, and low pressures. So KMT assumes that all gases are under these conditions and are behaving ideally. So the volume of gas particles themselves are not significant. This is assumed because the volume of the container is extremely large compared to the size of the molecules. And gases do not experience IMFs. This is assumed because at high temperatures, they're moving so quickly, IMFs don't really have time to happen and form. So gases behave less ideally and more what we would call a real gas behavior at low temperatures and high pressures. So as pressures increase, the particles are pushed closer together, which results in the volume of the gases being more significant. We can no longer ignore the volume of the gas itself. And as temperature decreases, the particles are moving slower, and that allows IMFs to happen. We have two competing theories, one where we can ignore IMFs and the volume of the gas, that's what we call ideal behavior, and one where we can't ignore those, and that's what we call a real gas. So this little chart summarizes those concepts. So, does it exist? Ideal gas do not exist. It's a hypothetical. And the gases that come closest to being, quote, ideal are hydrogen, helium, and nitrogen. But again, that's behaving ideally, because ideal gases is a hypothetical pretend situation where everything is perfect and IMFs don't exist. In real life, all gases are real gases, and they do experience IMFs. So the next line says, does it obey PV equals N? And when we assume that we're in ideal conditions or observing the ideal gas law, the ideal gas law works at all pressures and all temperatures. Real gases only obey the ideal gas law at low pressures and high temp, which is what we talked about a second ago. The volume is not included when we talk about ideal gases. In fact, the volume is ignored. But in real life, hence real gases, IRL, the volume of the gas is not negligible, and we actually need to factor that in. And then the last category is on IMFs. It says there's no force of attraction between gas particles. That's an assumption we make when we're talking about the fictional ideal gases, but in real life, IMFs must be considered. So you might be asking yourself, why do we have ideal gases if they don't really exist? And that's because we can force them to exist. And that goes back to these conditions that it points up here, high temperatures and low pressures. That is what allow us to use the ideal gas law. If we don't have those conditions, we cannot use the ideal gas law, and the math and the calculations becomes much more tedious. So a lot of times, scientists and chemists, when they're doing experiments, will make sure that they're in ideal gas law conditions so that they can use the ideal gas law. They're going to ensure that we're at high temperatures, and we're going to ensure that we are at low pressures. And so in picking those conditions, when you do an experiment, that's what allows you to use the ideal gas law. So let's look at some example problems. It says, which will deviate more from the ideal gas law at high pressures, a large particle or a small particle? So they want to know which one will behave more like a real gas. And it's going to be the large particle. And the reason is because, we can put a little because, we cannot ignore the volume of the gas particle at high pressures. Only at low pressures can we completely ignore volume. Obviously, the larger particle takes up more space than the smaller one does. All right, number 2 says, would you expect the predicted pressure of a sample of CCl4 to be closer to the predicted pressure compared to a sample of CCl4? So basically, based on calculations, we can make predictions of pressure. And they're asking which one would be closer to the predicted value. And they want us to compare CCl4 and CH4. The thing about these is that these are both going to be nonpolar because their dipoles cancel out. Well, on chlorine, the dipole cancels out. And on the CH4, we consider carbon-hydrogen nonpolar. So both of these are nonpolar. We probably could make an argument that CCl4 is a little bit bigger. We could also make an argument that even though they are both nonpolar, the CCl4 has a more, we talked about this earlier, more polarizable electron cloud. That's a fancy way of saying it has more electrons, which makes the London dispersion force, or LDF, stronger. If the IMFs are stronger, what that causes is the collisions, they're less elastic. They're not just going to simply bounce off each other as they would if there were no IMFs. And what that's going to do is causing the pressure to decrease. So I would say that CCl4 is going to deviate more from its predicted pressure. Next we have N2O and CO2 have similar molar masses. Which gas would you predict to deviate from an ideal gas? So we need to draw them. And for carbon dioxide, we have a linear shape. And even though carbon-hydrogen is considered a polar bond, we have offsetting polar dipoles, one pulling this way and one pulling this way. So again, this is going to be nonpolar. N2O, though, has a Lewis structure that looks like this. And this would have no dipole because nitrogen and nitrogen cancel each other out. But we are going to have a dipole between nitrogen and oxygen, and the electrons are going to pull more towards the oxygen end. So I would make an argument that this is going to be polar. And so which gas would you predict to deviate more from an ideal gas? I would predict that N2O would deviate more because it has stronger IMFs. And again, it is the same reasons that we talked about before. If the IMFs are stronger, that means they're going to be more attraction to each other. The particles will be more attracted. And then again, causing fewer collisions and a decrease in pressure. All right, that is deviations from the ideal gas law. Some students like to memorize what we were talking about here at the beginning with the conditions. When do we behave ideally and when do we behave more like a real gas? And I like to focus less on memorization and more understanding bullet points. If you understand the bullet points and what IMFs do and how they cause attraction between particles, you shouldn't have to memorize the conditions of when something's ideal or when something's real because you should be able to reason through that, thinking like, okay, at high temperatures, the particles are moving faster. There's going to be fewer collisions because it's at a lower pressure. And so that means that there's less intermolecular attractions. The particles are moving so fast. The volume can be disclosed because the volume of the container is going to be extremely large. So try to focus more on understanding the whys, and you shouldn't have to memorize anything here. All right, and that'll do it. I hope to see you guys next time for 3.7. Have a great day.